Welcome to the fourth and final user training video for Conjecture System Identification, a program that helps you take the data from your industrial systems and create simple models of best fit. In our previous training videos, we went through the main features of Conjecture System Identification and how to use the program to build and select models for a dynamic industrial system. We modeled systems with a single input and single output, multiple inputs, and looked at how to deal with systems with nonlinear properties. In this video, we're finishing up our training series by looking at some checks that we can do on our data and on the models we have fitted in Conjecture to evaluate how well our model reflects our process and, if not, how to improve its fit. We'll look at patterns of poor fit, what they might mean, and what we could do to fix them. Finally, we'll talk about how we determine the fit of our model with our overall process through a method known as cross-validation. In doing so, we'll recap some of the important points from the training series, and hopefully by the end of the series, you'll be able to confidently apply Conjecture to modeling your industrial system. As we've seen in our previous videos, it is important to look at the overall fit of our Conjecture model with our process. Check the peaks and troughs of the model. Do they reflect the peaks and troughs of the process output in terms of when they occur in time, as well as in magnitude? Here are some examples of models which are a good reflection of their underlying processes. In each one, the process output is shown by the blue line and the model output is in green. This first plot shows a model fitted to the first 800 or so time points of the multiple input pH system from video 3. You may recognize this plot as well from the air pump process in video 2. And this plot is of a ball and beam system that we built as an example of a nonlinear process. What these three plots have in common is that the ups and downs of the process are reflected well in the model, both in terms of the time points at which they occur and in their magnitude, how high and low the ups and downs go. Where the model doesn't fit the process well, we usually find certain patterns in how the model deviates from the process. Always zoom in on your model plot to the range of the data, and often if the fit of the model is poor, these patterns will be clear to see. There are just two patterns to look for. The first one is where the range of values of the model doesn't match that of the process. This plot, if you recall, came from the pH data from video 3 with two inputs. The model consistently sits higher than the process in some parts and lower than the process in other parts. And this is a clear indication that the system has nonlinear properties. The solution is to apply some type of transformation to the data, like we did in this case with a log transformation of the inputs. It is likely that many of the industrial systems you work with will have nonlinear properties, and so this pattern may be common, and a transformation will then be needed. We discussed transformations of the input and output data in more detail in video 2 on nonlinear systems. We saw another example of this pattern back in video 2 with our air pump system. Before we transformed our data, our model consistently sat lower than the process in some sections and higher than the process in others. Again, this system is nonlinear, and we found that we could only get a good fit by transforming the input and then transforming the output. And we talked about how to do this in video 2. The second pattern of poor fit that you might see is where the model generally follows the peaks and troughs of the process well, but sits either to the left or right of the process. In this plot, the model sits slightly to the left of the process, which you can see in some sections. And this means that we've underestimated the amount of delay in the system. The solution here is to refit the model in Conjecture using a higher input shift value in the model setup. If the model sits to the right of the process, as it does in some of the sections in this plot, it means that we've overestimated the amount of delay in the system. And so the solution here is to refit the model in Conjecture using a lower input shift value. Another clue as to whether or not your model fits well is the gain value in the Conjecture results window. As we discussed in previous videos, the gain is the steady-state change in the output that is associated with a 1-unit change in the input. Using this interpretation, we can compare the gain value we get with the known range of our equipment in the system and make an assessment of whether it sounds plausible. Note that if you've already determined that your model fit is poor, you should not rely on the gain. For example, in our air pump system from video 2, before we transformed the data, we got a gain value of nearly 52 cm that was associated with a 1% increase in the pump motor speed. Considering that the pump motor values range from 0 to 100%, while the ball height ranged only from 0 to 200 cm, the proportions just didn't make sense. Usually, good fitting models tend to come with sensible gains. Throughout this training series, we've talked about how to use the mean squared error, or MSE, to compare models fitted to the same process in Conjecture, with a lower MSE indicating a better fit. You can use the MSE to compare between different models built by adjusting the process dynamics in Conjecture or by making transformations to the inputs. An important point to note is that for the MSE to be comparable between models, they must have been built using the same output data. So you can compare the MSE between models of untransformed output, and you can compare the MSE between models where you've transformed the output. But they always must be compared between models that use the same output data. On the rare occasion, you may get a model that is an exceptionally poor fit to the system you're modeling. Even after you've tried transformations and adjusting the process dynamics, you could still get a really poor model. The reason for this lies with the machine learning algorithms behind Conjecture. These algorithms work by seeking out the minimum value of what we call a cost function, calculating better and better estimates of our model parameters such as a, b, little a, etc., starting with their initial conditions. In most cases, this works well, but on rare occasions, the initial condition is far away enough from this minimum that the algorithm can't actually get to it, and so we end up with a poorly fitting model. In such cases, we may need to adjust the initial conditions in the model setup. We've barely needed to touch the initial conditions before, but you may have noticed that where we checked the output shift box, the initial condition for the output shift is always set to 0. It may help in these rare cases to change this to a different value, such as the first process output value or the average process output value, which you can get from your data. You can do this in your model setup in the same way you would adjust any of your process dynamics. An important idea in machine learning is that of cross-validation. Cross-validation helps you assess how well your model reflects not only your data, but the whole of the process itself. Say you've taken one data set from your system and used it to build your model in Conjecture. Once you've built a model you're happy with, take a second data set from the same system, running on similar parameters, and apply it to your model. We want to assess whether the model is a good fit to both data sets. Cross-validation is important because it allows you to evaluate how well your model generalizes to your process at large, and how well it encompasses process variations like different grades of product, for example. How well does your model need to fit both datasets? Well, it all depends on how you want to use your model. One use that we at Conjecture Data Solutions like to demonstrate is to combine your model and process data using a complementary filter and use this to improve your PID control. Because a complementary filter uses both process and model data, even a less than best fit model can be incorporated into the filter and used successfully to improve control. However, if you're using your model for simulations of your plant, you'll want one with a higher degree of accuracy. If your model fits poorly across other datasets from the same system, you may need to consider a few fixes. Firstly, review your system and reassess the variables you've included in your model. You may be missing an important variable or doubling up by measuring the same variable across two different inputs. Secondly, consider if further transformations to your data may be required, again by looking at the properties of your system for nonlinear characteristics. And as a last resort, you may need to consider whether different variations of plant operation may best be reflected with different models, and build separate models for vastly different process variations. If you'd like a demonstration of how the conjecture model can be used to dramatically improve PID control of your industrial system, check out our video demonstration showing how we use a complementary filter to combine your conjecture model and process for the PID-controlled air pump system from video 2. A link to this video is included in the video description box below. This brings us to the end of our user training series for Conjecture System Identification. If you need further support, please do not hesitate to contact us at support@systemident.com. We would strongly welcome any feedback you have on the Conjecture program as well as these training videos, so please get in touch. We already have several upgrades planned and are committed to using your feedback to improve your user experience of Conjecture. For questions about licensing or to get more copies of Conjecture for your organization, please email admin@systemident.com and we can get you set up. We hope you found this training series helpful and look forward to hearing about what improvements you're making to your plant with Conjecture. Thanks for watching, and we hope you enjoy using Conjecture System Identification, brought to you by Conjecture Data Solutions.